All right, well, hi there, gang. We're going to talk today about that repeated process again, where you had to do integration by parts more than once. And it specifically applies, okay, so yesterday, you know how we talked about the LIPET, the Lipet rule. You will have repeated integration by parts when you are in the lower half of the alphabet, or the lower half of that, in a PET situation. So, and anytime you've got a P, that's a possibility of having a repeated integration by parts. It really depends on the P power. Okay, the higher the power, the more you'll have to do that multiple times. And then we're also going to look at a special case of what if you have just an E and a T combination. And that is another instance where you would have a repeated integration by parts. So if you start with a P and have either an E and a T or just an E and a T, those are going to be repeated application by parts. So let's take a look at this. This is actually the same example we ended with yesterday. Okay, so I want you to look at, we've got the P polynomial here. And then we've got the exponential. So this is a combination of the P and the E part. And the power on the exponential is a power 2, which means we would need a repeated use of integration by parts twice. So if that power is a 3 or a 4, you'll do it that many times. Okay, so just want to go through this again quickly with you. We're going to choose our 2x squared, which means the differential is 4x dx. And then the E part is e to the x dx with an antiderivative e to the x. So my original problem becomes, in the first round of integration by parts, 2x squared e to the x minus integration 4x e to the x dx. And I still have a P and an E combination. So that's where we do it again. And we'll have 4 dx then as our derivative, and then e to the x dx, the exponential, where the antiderivative is simply e to the x. So this part here becomes 4x e to the x minus the integral of 4 e to the x dx. That whole thing is behind this subtraction sign and the 2x squared e to the x, which was in front of that. So this subtraction sign then gets distributed. So we're looking at 2x squared e to the x minus 4x e to the x and plus a 4 pulled out of the integral of e to the x dx, which helps me to get in my final form, where the antiderivative for integral e to the x is 4 e to the x plus c. One other thing you might see with these repeated integration by parts is that often the answer is written in factored form. So I'm going to squeeze that in here. All of these terms are even. So we've got 2, 4, 4, and they also have e to the x. And so factoring out a 2 e to the x out of this expression would leave me with x squared minus 2x plus 2, and then your plus c. So it is pretty common to see an answer written in factored form as well. All right, so we've done that one now twice. Now here is what I really want to focus on today. Here is the combination where LIP, we don't have any of those, and we're going for an E and a T here in terms of our combination. So e to the x is our u, and then cosine x dx is our v term. All right, what's special about this is that e and t, exponentials and trig functions, are what we call cyclic functions. Right, and by what we mean by that is that their derivatives keep rolling over onto themselves. So e to the x, it just has a continuous derivative of e to the x, and then e to the x, and then e to the x. So its derivative is cyclic. Cosine is has a cyclic pattern to its derivative. We go from cosine to negative sine, and then its derivative would be negative cosine, and then that derivative would be positive sine, and we'd back to negative positive cosine. It's a cyclic cycle. And so when both of those happen, you're going to need a repeated integration by parts again. So let me show you how this is going to work out for us. So we've chosen our u and our dv. And so the differential is still e to the x dx, and the antiderivative is sine of x. So we've got our question, which starts out as the first integration by parts. So we'll go this direction. So e to the x sine x minus, and then our horizontal combination here, e to the x sine x dx, which gets me into another situation of an e and a t. So I've got the exponential part here, and then I've got the trig part here, so another e and a t combination. So I'm going to do it again. The exponential, and now my dv part is sine of x dx. So that'll be e to the x dx again, and then the antiderivative of sine of x is negative cos of x. Okay, so that combination, so that's going to give me this integral becomes negative e to the x cos x minus another negative e to the x cos x dx. So double negative here. Now remember, that whole thing is behind this negative sign. And also, e to the x sine x is in front of that, and in front of that is the original question. So that negative that's got the red arrow, that will get distributed to the rest of my, it'll get distributed here. All right, so let's maybe just take care of the negatives and the distributing. So I'm going to erase. All right, so this is now a plus, and this is a minus. Okay, now you notice that this integral is another e and a t combination. But notice how it cycled back to the exact same e and t combination we started with. Okay, it's back to the very original question. So in other words, let me see if I can do this for you guys. This e and t combination is exactly the same as the original e and t combination. So we call those like terms. And if those terms are like terms, they can be added together. So I'm going to add this particular integral to both sides. And those two integrals added together are 2 times the integral of e to the cos x dx. And on the other side, I'm left with e to the x sine x plus e to the x cos x. Oh, and I forgot my plus c. I should have had that in there. So notice now the right side of the equation has no integrals at all. I've managed to get rid of all the integrals. I've got e to the x sine x plus e to the x cos x plus c with no integrals on it. The only thing I've got is this 2 hanging out here. So if I'm going to solve this equation and get this integral by itself, I need to divide the whole problem by 2. So that tells me that e to the x cos x dx, which is the question I started with, is equal to e to the x sine x over 2 plus e to the x cos x over 2 plus the constant divided by 2, which is still a constant. And so that's my answer. I've gotten the original equation equal to something that doesn't have any integrals in it. This will always happen in an E and a T combination, this cyclic thing. It should take 2 cycles before your E and T combination matches your original E and T combination. It should only take 2 cycles for that to happen. And then you'll combine the first and the last integral. So you'll combine whatever you started with, and this should be the same combination and allow you to add in such a way that you can add those integrals together. All right, so your work is still integration by parts, but you're going to be dealing with situations where you have to do it more than once, okay? And then when we come back together next week, we'll have our last day on integration by parts here in 6-3, okay? So I hope you have a good weekend, and I look forward to seeing you guys on Tuesday.